G'day, Michael here. This video is about woodwork, the basics. I see all the time evidence of people not really understanding deep down what's going on with timber and wood. Well, wood is the term, I suppose you could call it the stuff that we're working with, but timber is actually the term of wood that's been made ready or is usable or suitable for making something out of. A good comparison is firewood versus a piece of timber to make a door out of. So there's probably a little phrase there that describes the meaning difference. Any fibrous material from a plant that has a kind of structure, that has a woody structure, can be called wood. But not all wood can be called timber. Timber is something better for making things out of. Wood is just a very general term. Now, wood comes from a tree. I'm sure you're familiar with what a tree is. But what you may not really understand about a tree is a tree kind of grows as a cone. It might have a root form in its simplest form, and it's a cone. And then from that cone there might be little cones that grow outside. The reason why I say cone is to kind of simplify what's going on with the tree, and that might fork more and more often. You can even look up videos on fractals and you'll have a kind of an understanding of what goes on. But as it grows, I'm going to say every year because it's not strictly true, but let's say every year it grows another layer on the outside of all those bits. And so you can see the tree, it basically grows in layers. And what you see with wood is growth rings. I'll just grab a piece of wood. Okay, so you can see here the way the grain has worked. You'll have the cone that is growing from below that forms the trunk, and then a branch that's come off this way, and that branch is another cone growing off another direction. So what you have with timber is fundamentally, it is not a straight material for starters. It is a conical material, and of course with branches to complicate matters. But in its simplest form, it's just a cone which grows extra layers on the outside. Go back to our little drawing here, and as it grows more little branches, and those branches grow layers each year. It gets more and more layers. This is getting too complex for me to draw, but you can see how the growth works over the whole area. But what happens is, in the forest, generally they'll be managed forests, they'll minimise the amount of branches that are on the trunk, or they'll plant a type of tree which generally grows, let's say it's a root system, which generally grows a longer and longer trunk, and any branches that are trimmed off will be grown over by a new layer, and the branching is kept as high as is possible, because all we can really use is this portion of the log that's fairly straight. If it's too crooked, then it becomes unviable for making anything out of. But you still do have a conical section. It is not a straight section. So with timber, that produces a whole raft of issues to deal with. Now, the guy that has to cut up the log to produce a decent piece of timber is dealing with looking at an end section, a round log, which is a conical section that gets narrow towards the other end. So imagine looking down the log, you're seeing a cone. But as we saw with the growth lines, it's actually a cone that's grown out in layers. And then the outer layer is actually whatever's new on the tree, and that's basically what's called sap wood. And outside of that, of course, is the bark. But we can't use a sap wood because it hasn't really stabilised. It's actually undesirable for any structure. It might be okay for figure, but it's not really that usable for structure. So anyhow, when they're cutting up the log, they've got to try and work out a way of maybe cutting up the log that yields a fairly good number of relatively square sections. And you can see the problem that I have here with this excessively conical piece. There's all these lost sections on the side which can't be used to make a rectangular section or a square section of timber. So there's a lot of losses. Now, obviously the conical section is a loss, and the circular section going from circular to square is also a loss. But there's a whole other lot of problems with that. But in any case, bear in mind when you're getting timber, someone has already gone through that process of trying to work out how to get the most out of the log. But understand that that means that the various pieces of timber are going to have different grain characteristics. Now those grain characteristics, I'll just clear this board. So there's our, our circle going down it progressively smaller towards the centre. Roughly the growth rings get finer as you go out, simply because it's putting more and more, I want to say, tonnage on the tree as it gets larger, and it's being spread out over a bigger area. So it may actually be growing more as it goes to the outside edge, in kilos or tonnage, whatever you want to call it, but the grain lines generally get finer. You can see on this particular section it's actually fairly close to the centre of the log. The centre of the log's about, I don't know, about there somewhere. So it's not far away from the centre. Okay. Now the centre of a log is what's called the heartwood. So we had sapwood on the outside where it's alive or maybe just a year or two old, which is already starting to become dead and set wood. And you've got the heartwood, which is kind of like a soft core from when it was an initial sapling, like its original growth. So this is an undesirable, weaker and less stable piece of material, and the outside sapwood is also undesirable and weaker. But going back to our cutting it to sections, let's make this as simple as possible. Maybe a cut through here, maybe a cut that way. Let's just do that. You can see that's done in quarters. Okay. Now what we have is, looking at the side of the board, when you would take this out, you'd see all the grains spaced out evenly for what the growth is. And that is called quarter sawn, where you see the grain fine from the side. So if you look at the piece of timber from the side, it would just have vertical grain lines doing that, very close together. If that makes sense. Right. So that's called quarter sawn. Right? Now, if we have a cut like this going through, you can see this piece here has got the grain lines coming in at quite a flat angle towards the centre. Now that's called back sawn. I might just move the camera down a tad so I can show you another drawing. Okay, so what that would look like is, let's say this is our plank in width. We have grain lines doing this kind of thing, and you would have seen this on timber. That's because the timber is basically a cone, and you've got these very flat curves coming in to the edge. Going back up here, I should show this here. So you can see here, as these circular halves or grain lines coincide with the surface of our cut, we get this business happening, and that's what's called back sawn. So that's how you can recognise looking at it visually. And of course, the timber is not actually cut that perfectly. The various sections would not necessarily be cut that perfectly. Some of them are cut over here, so they've got kind of a 45-degree angle to the surface. So this is back sawn, that's quarter sawn, and you get a variation anywhere in between those things. But in any case, from that you learn where the heart is. Now looking at the end grain of this piece here, like let's say this is a plank in your hand, well actually that'll be sap wood and discarded, but let's say it's a plank in your hand and the plank is this big, right? The grain will be doing that. So you can see where the heart would be just by sort of following the circular line like I did with that piece of timber a minute ago. Okay, having another piece like this piece, with the grain doing that, you can see that obviously that's pointing to the grain. Or if we had a piece that's there, you can still see where it's pointing to the sapwood. Now it's important to know where that, not sapwood, the heartwood. It's important to know where the heart is, because what happens with timber movement, the sapwood is more full of moisture because it's closer to the living tree. The outside bit, the bark, and working out from the bark into the sapwood is the living part of the tree, full of moisture because that's what it runs on, that's what it operates with. Okay. But as you get towards the centre, you get the older, drier part of the timber, and the centre obviously is kind of stabilised out to whatever the relative humidity is of that environment. Depending on where the timber is in the world, that may vary quite a bit. Like it might be somewhere like 30% in a tropical environment, maybe even a bit higher. But in say our neighbourhood, say Canberra, is about 11%. Where I am right here is probably about 14%, because I'm getting closer to the coast. But that can vary. If we have an extended period of drought, the moisture in the air, the general humidity drops down. So it's all measured in relative humidity. I'm going to leave that aside, but just know that there's a moisture component to the timber. It's not just a static material like maybe a piece of steel. Okay, so knowing that the outside is more moist and the inside is drier, what happens is after the log is cut, I'll let the pen go dry, after the log is cut, this will shrink on the outside and the centre will shrink less or maybe not even at all, and so it produces a cupping in the plank. Not only that, it produces a bit of a taper. Have I drawn that clear enough for you? So, yep, you can see how it's, there's a taper. The centre bit here stays about the same, but as you get closer to that higher humidity or higher moisture level, the material shrinks. So a back sawn piece of timber that looks like this will bow like my little drawing here. That may not even be an exaggeration of what would really happen from a freshly cut log to a piece that's dried out. That might be actually quite a fair representation. Now with the quarter sawn piece, this here shrinks and that doesn't shrink very much. So I actually end up with a board that slightly tapers. That's a bit of an exaggeration there, okay? But that's the sort of thing that happens. So understanding how the timber moves gives you some insight as to what you've got to do to build in an allowance for it to move. When we work with timber, the design has to allow that timber to move, and this is the biggest fault I see in things that are made with solid timber by people that don't understand timber. So if you take away anything from this video, this business that I've just gone through with the shrinkage and the movement, that's probably the most important thing to walk away with as far as understanding a long-term, a longevity of your product, whatever it is. If you don't build in something that can allow for that movement, you'll have a very short-term product on your hand. A chap I know built a door, not building in this allowance for movement, and within the year it self-destructed. Now he did a wonderful job as far as all the effort he put into it, but because he didn't understand the timber, he created something that self-destructed within the year. And that's very easy to do if you don't make allowances for how timber behaves. And that's a very big important part. Essentially timber is tubes, whole lots of little tubes to make up the grain. And timber is, and wood is grouped into two areas, two types. One is a softwood and one is a hardwood. Now it has nothing to do with the softness and hardness, it has to do with the cell shape or the cell structure. Balsa, for argument's sake, which is quite light and quite soft, it's used in model aeroplanes and that sort of thing, that's actually a hardwood. Something that's, well, this is Douglas fir, North American timber. It is a softwood. And the Douglas fir is a lot harder than balsa and it's a lot heavier than balsa. So don't be confused by how hard the material is. It's the cell structure. Now I'll draw as best I can a representation of the difference. Okay. Now hardwood is this kind of thing going on where you've got circular cells with varying sizes. I hope that shows up well on the camera. So this is very typical of a hardwood structure. It's kind of circular with varying sized cells. Now the general amount of, the general size, the general density varies according to how it grows. So maybe in a warm and humid time of the year you'll grow quickly and so the cells will be larger. In a harder to grow, maybe colder or drier period where it cannot grow as fast, the cells become smaller, and that's what produces the growth rings as the tree grows, and it tends to be a yearly cycle. So people date trees by their growth rings, although really that could be in areas where it's maybe tropical. It may not necessarily go exactly with years. It will certainly go with the changes in the growth speed of the tree. Yes, that's a bit, well, I would pretty much I'm going to say almost always be true that it'd be a yearly change. It may not be. Alright, now that's hardwood. Now softwood is kind of like, well, kind of like brickwork. So the cells grow almost in a square kind of pattern, a bit like bricks do. Bricks, you know, overlap and interlink like that. Okay. Now a drier time of the year makes the cells a lot smaller, or you know, a slower growing thing. So you've still got the same kind of rules affecting growth rings on both types of wood. So you've got to change in the growth rings by how quickly it can grow. So you have a hardwood structure and a softwood structure. That's basically the difference between the two. And you can imagine these circular structures are much better for like cutting. They tend to chip out less, etc. and more consistent, and generally they're harder than a rectangular structure, which is more prone to being crushed or broken or torn. And you will notice actually, because I can get a good. Now this is a softwood, like I said, a Douglas fir, and you can see this kind of breakages, even on this camera. I think you can see it. How much I can wring out of this camera. You can see this is cut quite well. You can see the breakage in the cells. Where the growth rings are harder, there's less breakage, and where it's softer, it's fractured up. Now this is a particularly good blade. Put this way, a cut veneer, and on the underside it's very unlikely that it chips out. I'll just grab a bit of plywood, maybe, to show you the same thing. This is a piece of plywood cut with the same blade. Now this is an Australian timber, hoop pine from Queensland. And you can see there's very minimal tearing out with this particular blade. And what we have with plywood is grains going across each other. Now in plywood this principle works. If you intend to make this sort of cross-grain business with a large piece of timber, you will have something that will self-destruct very quickly. Okay, so I'll explain what I'm moving on to with the self-destructing structures. When you may have actually seen in any traditional timber work where you've seen a door made, you may remember seeing a door. It's not made out of one plank and just, you know, cut to size. It's made with two verticals on the side, and they're called stiles, two horizontals, which are called rails, and then you'll have a panel which will typically have kind of what's called a fielding cut in it, like it's a thinner little bit on the edge, and you know, it might look a little bit like this, and it may be, I don't know, joined out of a couple of planks, and you might have, you know, a decorative figure, whatever it might be. So it'll look something like that. Okay. Now that's done to be decorative, yes. Oh, that's very wonky. It's done to be decorative, yes, but it's also done, more importantly, these rails, these are called stiles, the verticals are called stiles, and the horizontals are called rails, and the panel is called a fielded panel. Now, if we look at the rail, I'm going to blow it up so it's a bit visible here. The bottom rail will have a section something like this in it, where you've got a groove in the centre. And it's usually very close to quarter sawn, or, you know, something like that. So these are grain lines doing their thing. Okay, so there's that grain line. The fielded panel will tend to have a bit of a shape to it like this. And there's the larger flat area. So we're talking about this little area here, sort of in section, that area there, looking at it through the section. Okay, so the rail has got the groove, and the fielded panel is just to make a thin edge that will go in that groove on the panel. But fundamentally the panel's a thick panel, so it's fairly strong, but it's got a thin down edge to go in the groove. Now that panel is in that groove so that it can slide, so it can move. So as the panel expands and contracts in width, it doesn't have a conflict with the rail. Now timber moves a lot in width, but it doesn't move much in length. So across the grain there's quite a bit of movement, but in length there's almost none. In fact, for all intents and purposes, you can call it none, right? So this bigger area of movement here is quite substantial. It may be a few millimetres over a year. It's quite a bit. But if you had the panel held solid, it would split, self-destruct somehow. And this is what I mean by self-destructing structure. If you have a big solid timber slab and you put solid timber pieces around the outside, a frame around the outside, you will have a broken joint somehow. Either the joint between the wider panel in the centre to the rail would break, or the panel itself would break in pieces to be able to maintain its joint with the rail. So this business has to be able to slide. It's a very important detail. Not only that, and if you look around your house, you've probably got some timber frame doors somewhere, and you'll be able to verify this point yourself. If the rail is quite wide, if you happen to have a door that's got a much wider rail, let's just get rid of that detail for a second, and you've got another rail that's much narrower, have a look at the wider rail and you'll find there'll be areas of some sort of breakage, some sort of movement, where the expansion and contraction of the rail has actually broken that joint a little bit. The narrow one is much less prone to it. There's always going to be movement, so it's a matter of how much, not whether or not. If the thing's 30 years old, you will probably see a significant amount of this. Another thing that happens too is, I've seen it often enough, where this rail is no longer flush with the stile. It's produced a step, or it's shrank away or whatever. Depends on whether your environment is now much more humid or drier than what the timber was initially. So if you move from, say, I don't know, a tropical island to the centre of Australia, you'd have a lot of shrinkage here and you have a lot of parts breaking up. So, going from, I don't know, Hawaii to Arizona desert would be the same sort of thing. So it's quite an important thing to understand. The narrower you make those joints, the less prone they are to breakage. This is all very important, but it all comes back to our little cone that is wetter on the outside than it is on the centre, and there's a soft, weaker heartwood, which is also something you need to build out around the structure, build away from, and allow for the timber to do whatever it does, rather than trying to constrain it. I guess that's a very important part of it too. When you're working with timber, if a joint doesn't fit when you go to glue it together, don't glue it together. Make it fit first. When it fits, then glue it together. If there's tensions on that glue joint, when you're putting it together, it will fail. If the timber is basically free of tensions, when it goes together, it's got a very good chance of lasting, indefinitely. So it's very important to not artificially force timber together when you're joining it up. It's important to make sure it works properly by itself. Okay. Now coming back to the fact that the structure of the timber is actually lots of tubes, that might give you an insight as to, if you start thinking about that, how you need to cut wood. This is a big area that I also see this, a lack of understanding in how to cut wood or cut timber. You can probably imagine something like a bundle of straws, maybe. That'll help. Let's put some depth to this. So this is actually what our wood structure is like. We've got tubes. If we go to cut that off, obviously if we use some sort of knife to go this way, what will happen is we'll just split it. And I'm sure, if you've used an axe to chop wood, you'll have seen that how it works quite simply. It just separates the tubes and they basically just fall apart. But what will happen is your cutting tool will follow whatever the curves and whatever is going on with the growth of the timber. If there's a lot of twists and turns, your axe will follow the twists and turns. So that's not a very ideal way of cutting wood, because you're at the mercy of how it's grown. You have no control over where the cut happens. Okay, so we can't do it that way. So what do we have to do if we're going to cut down the length, and we want to cut a direction that we want to cut rather than the way the timber wants to cut? What do we have to do? Well, actually, we have to kind of disregard what it wants to do and not think of it as a cut that way. Well, I've actually got to break each cell, like we've cut off the cell in length. We can't just split it, we have to cut it off. Now, it makes sense if you imagine a bunch of tubes and we're going to have maybe a cross cut, we want to cut across there, right? We could use a knife and cut across and we'd get through a few layers of these tubes and then cut a bit more and a bit more and a bit more, and that's actually what we do when we cross cut. We cut off the tubes that way. But if we're cutting this way, we need to sort of chop them off in portions at a time and sort of, like, I'm going to say, chew a little bit off in length. And so if you start thinking like that, that's how a rip saw works, or a circular saw. Now the rip saw and cross-cut saw uses those two different properties to, like, score off, if you're cross-cutting, score off the tubes, or chisel off the tubes if you're doing a rip. Now I'll show you what I mean by that. If we want to cut down the piece of timber lengthways, we can do this. So we're chopping off the cells and we're working our way down the timber. So that's actually how you've got to cut down the length. So that's a successful way of getting down the length of the timber, and that's basically how a saw works. Of course, the saw is more optimised and more efficient than my chisel is for this particular job. Okay, so in either case, we've chopped off the cells. If I use the same tool and try and go the other way, let's see what happens. Oh. As you can see, it's separating the cells, splitting them apart, but it's not actually cutting the timber exactly the way I want it to. So I'm executing a method which emulates a rip saw cut. Now this way, it's obviously unsuccessful, whereas going the other way was successful. Why? Because in this case, I was cutting off the cells, and this way I'm splitting the cells. Okay, let's get a fresh bit of timber. Let's say we want to emulate a cross-cut saw. Just use this chisel best I can. Okay, so I've actually just cut the cells off. Now let's just do the same again here. So 2 cuts and I'm starting to break away the wood. So as you can see, if I keep doing a process of however rough this method is, it's actually successfully cutting across. So that's, as you can see here, the method for cross-cutting. Now a blade that's better designed for cross-cutting, obviously it's much more efficient than my score method with a single blade, but that's basically what's going on there. Now let's have a look at the teeth. You can see how these teeth got quite a layback kind of angle in the teeth. So it's more like having a knife blade cutting off. So I'll just emulate that. It's quite effortless in the way it cross cuts, and that is for the same reason that the using my chisel like a knife to cut off the cells works. It's got that layback or negative rake, and it's actually quite a sharp. Let's see if I can show you this. The edges are actually cut at quite an angle to the path of the blade. So, okay, so hopefully that little example made a bit of sense to you. But basically all you're ever doing with woodwork is to always cut off the tubes. You're never splitting the tubes. If you split the tubes apart, the cells apart, you end up with an unpredictable cut. If you cut the cells off, you end up with your desired result. So those two principles where I showed you kind of chiseling off a channel progressively along the length while still cutting off the cells. Using cross-cut method was still cutting off the cells, was never splitting the cells. The only time you can split cells apart is if you've began chiseling something, so a mortise hole, and you want to just get rid of the material in the middle. But beware with whatever you're doing when you're cutting that you may be inviting disaster. So just be aware you need to cut off the cells to maintain a predictable sort of a cut. And if you're trying to separate the cells by splitting it off, you've got a less controllable cut. Let's say this is our very rough looking handsaw. Handle this end, right? A cross-cut tooth will be quite a lay-back tooth. I'm exaggerating the angle so it's very visible. Okay, so it's very much lay-back, so you're using like something like a Stanley knife in effect to cut the timber cells off. But you also want to have quite an angle so that the cells are confronted with a kind of a knife edge. So similar to our knife edge to cut the pieces off. And this is a very rough representation of a saw. It'd be very, very hard to drive. But yeah, that's basically our situation. So we've got alternating teeth acting like knives to slice off the cells. So this would be good for cutting across, but it'd be no good for cutting along. So let's do another garden variety rough looking saw. Now a rip saw wants to be like the little set of chisels, sort of progressively digging the cells off. So it's quite an upright angle. And quite square through. So looking at these saw blades from above, this one's more interesting, the cross-cut blade. Looking at it from above, let's say this is the thickness of the blade. Let's see if I can draw that reasonably well. You need to have what's called a set on the blade so that the teeth stick out either side. Because you're cutting a fibrous material, the fibres kind of break off and then bend back into space. So the teeth need to be bent over a little bit, either way. So one tooth bent this way, and the other tooth being bent the other way. So you end up with the actual working area, or the kerf of the saw cut is the distance between the tips of the teeth. But because the crosscut's got these bevels, you actually end up with this kind of business in the furrows. Yeah, so it's hard to draw from above, but in essence you've got angled edges producing a sharp point cutting off the cells, whereas the ripsaw blade is just simply square through to try and like chisel off the cells. So you can look up the details of angles that people have used. There's lots of different designs, but in essence all you're ever doing is like chiseling off when you're trying to chop off the cells by going down the length of the grain, or you're trying to kind of knife off the cells and you're cutting across. Of course, when you're cutting through a knotted piece of timber like the other piece I had earlier. So if you're trying to cut through this, where you've got everything going on with the grain, you kind of need a balance between the two. So you kind of want a cross-cut blade and a ripsaw blade combination, a very general purpose thing. Or simply lots and lots and lots of fine teeth to try and make a reasonable cut out of it. Okay, I hope that video was of benefit to you. Trying to cover the grade clouds at the lowest level on woodwork is something I haven't really seen anyone do anywhere, and I'm hoping this video covers that. Well, feel free to like, share, subscribe, ask a question, leave a comment. Bye for now.